Hello everybody. In this lesson we are going to be dealing with the revision of trigonometry from grade 10. So before we move on to grade 11 work, first things first, we need to understand that we need to revise on the stuff we've learned in grade 10 and we're going to use that into the grade 11 content where we are going to be learning some things such as identities, you'll see what it's about, the reduction formula, so how to reduce the trigonometric functions, and also solving trig equations. So let's get started with the revision. First things first, we need to look at the trigonometric ratios. So SOHCAHTOA is one thing that we are going to be using. So SO, meaning sine, is equal to, you're going to have to follow the order by the way. It's going to be sine is equal to O over H, which is opposite over hypotenuse. So if we were to put this into translation, sine theta is equal to opposite, which I'll represent as op, and hypotenuse as hype. Okay, so it's first SO, then CA. So SO, CA, and C would stand for cos. So cosine theta is equal to AH, meaning adjacent over hypotenuse. Remember that these are representing the sides with a relationship to the angle, meaning the relationship with the angle theta, we are going to be dealing with the opposite side divided by the longer side, which is the hypotenuse. With cosine, it's going to be the adjacent side, which is going to be the one next to the angle, over the hypotenuse, that's the longer side. So it's ADJ over hype. Okay? And then the last one is TOA, which is tan. So it's tangent theta is equal to, it is OA, which is opposite over adjacent. So it's going to be the opposite side divided by the adjacent side for the angle theta. Remember, we're dealing with the relationship with theta. And obviously the trig ratios are there. So you need to just remember that. So now we have our special triangles, or we can refer to this as special angles, right? Because usually if you get questions that says calculate without a calculator, right? So solve the following without using a calculator, then you will be using these special angles. And when we get into reduction, you'll learn that you're going to be given bigger angles which you need to reduce to get these angles and use the special angles to evaluate without a calculator. But we'll get into that later. For now, let's use the trig ratios to actually show what makes these so special. Okay, so first things first, we note that all these angles add up to 180 degrees because it's a triangle, right? 90 degrees here, 45, 45. 90 degrees here, 30 and 60. The first triangle over here, it's the easiest one to remember, so it's both 45 degrees of an angle, and we have 1, 1, and root 2. It's not 2, it's root 2 for the 45 degrees. The second triangle, we have 30 degrees and 60 degrees, but instead of root 2, now we have 2. Here we have 1 and root 3. Usually, students would forget about where to put the root 3, whether they should put it here by 30 degrees or 60 degrees, because when they're in a test or an examination, they're under a little bit of pressure and sometimes they'll forget which one. The best way to remember where to put the root 3, in my opinion, is to look at the 30 degrees. It's always going to be adjacent to each other, right? Do you see the number 3? Put the root 3 wherever 30 degrees is, adjacent to 30 degrees. That will make life much more easier for you. And then that's just something that's one of the best ways that I could say to kind of memorize, even though memorizing isn't super good. When it comes to those moments that you need to save yourself, obviously this is the best approach that I have at the moment. Okay. Otherwise, let's just use trig ratios to actually evaluate without a calculator what you would actually expect and how to read these triangles. Okay. First things first. What about sine? What's happening with sine? So let's say sine of, we're working with 45 degrees for the first triangle, okay? So sine of 45 degrees, also don't forget about the degrees, by the way, that's important. Sine of 45 degrees, that is going to be what? What did we say it was? SOHCAHTOA. It's sine is equal to opposite over adjacent, opposite over hypotenuse, right? Meaning, we are going to take the opposite. It doesn't matter which one you take. They're both 45. It must be the opposite, which is the side opposite to 45 degrees divided by the hypotenuse, right? So it's going to be 1 divided by the hypotenuse, which is the longest side of the right angle triangle, or the opposite side to the right angle, okay? So it's going to be 1 over root 2 because it's opposite over hypotenuse, or sine. What about cosine? Cosine of 45 degrees is going to be adjacent over hypotenuse, right? SOHCAHTOA. C is equal to A over H. So now, what we're going to be doing with this one, we're going to take the 45 degrees, it's going to be the adjacent divided by the hypotenuse, which is also going to be 1 divided by root 2. And then the last one, which is tan of 45 degrees is just going to be equal to, it's going to be opposite over adjacent, right? So opposite over adjacent, it's going to be the opposite side divided by the adjacent side to the angle, meaning it's just going to be 1 divided by 1, which is just equal to 1. Okay, so tan 45 degrees is just equal to 1 in this case. And if we were to use the bottom triangle, there's two different angles that we can use, right? The first one we had 45 degrees and 45 degrees, but this one we have 30 degrees and we have 60 degrees, okay? So let's do 30 degrees first, okay? So we have sine of 30 degrees, which is equal to, remember sine is opposite over hypotenuse, so it'll be the opposite. It's going to be the opposite, which is 1, divided by the hypotenuse of 30 degrees, which is 2. So it's going to be 1 over 2, which is a half. Okay? What about cosine? Cosine of that 30 degrees is just going to be adjacent over hypotenuse, right? Meaning, we are going to take the adjacent side, which is root 3, over the hypotenuse, which is 2. Meaning, we are going to have cos 30 equals to root 3 over 2. And now tan. What about tan? Tan of 30 degrees, we know that tan is equal to opposite over adjacent, right? So opposite over adjacent, it's going to be 1, which is the opposite side of 30 degrees, and the adjacent, which is root 3. Okay? So it's going to be 1 divided by root 3. Now we can move on to the 60 degrees, okay? So sine of 60 degrees, we know it's going to be opposite over hypotenuse because it's sine. And now we're actually paying attention to the 60 degrees. So let me color code that. So now we have 60 degrees, right? The opposite of 60 degrees is just root 3, and the hypotenuse is 2. Okay? So that means we are going to have root 3 over 2. Cosine of 60 degrees, we know that cosine is adjacent over hypotenuse, so which means we're going to take the adjacent side divided by the hypotenuse, which is just 1 over 2. And then the last one, which we're going to be dealing with this part, is going to be tan of 60 degrees. We know that tan is opposite over adjacent, and the opposite to 60 degrees is just going to be root 3, and the adjacent is just going to be 1. So what we are going to be having is root 3 divided by 1, which is the same as root 3. Okay, so that's how we evaluate using triangles. I just wanted to teach you how to look at triangles and be able to deduce what is the opposite side, what is the hypotenuse, and how do we actually use these ratios to evaluate. Okay, so let's get into one more part of the revision, and then after that, we are going to be dealing with some examples to end off the lesson. So here we are now. We need to deal with a Cartesian plane, but also use trig ratios, okay? So suppose we have some type of radius, which we call r. Let me do it in a color red, so that we can see what's going on, right? So we start from the origin, and then let's just put it here, okay? Now we're going to see that it ends at this point, okay? And this is the radius r, assuming we have some type of circle, okay? So what do we notice here? When we're dealing with trigonometry, usually we're dealing with right angle triangles. So why don't we just try and form this into some type of right angle triangle? And how do we do that? If we take the point from the last point of the radius from the origin, if we go down parallel to the y-axis, okay, what you notice, we have it parallel to the y-axis over here, but that is actually just going to be the height from the x-axis all the way to the y value at this point, right? So that is the height, and we call that y in our coordinates. And then this part over here, right? If we want to go from the origin all the way to this point here, that would be called the width, or the distance from the origin to the point over here, okay? And we'll call that the x, obviously, because it's going to be going along the x-axis. So if we put that into writing here, this would be the height y, okay? This is just our convention. And then this part over here is just going to be our width, x, of the rectangle, of the triangle. And notice what we just did. We just formed ourselves a right angle triangle where we have x, we have y, and we also have r. Notice the x is also parallel to the x-axis, so that's also why we call it x. So here we have an x and a y. Okay. Now, how do we actually correlate this to trigonometry though? Like the trig ratios. Now, we need to convent a theta. We need to construct a theta somewhere. Let's say that theta is going to be here. Okay, and let's assume positive orientation. By the way, this anti-clockwise orientation is always positive, and if we're going from here all the way to that side, it's always a negative orientation. Okay, but for this one, we just form theta, right, for the right angle triangle, if you remember from our trig ratios. And now we need to find out what is the ratios of sine, cos, and theta, and tan going to be. So here, let's deal with sine. So sine over angle theta is going to be equal to what? Remember, sine is equal to opposite over hypotenuse, right? What is the opposite of theta? It is just y. Okay, so I'm going to do it in pink over here. Opposite to theta is y. Alright, and the hypotenuse to theta is r in red. So which means we're going to have y divided by r in terms of Cartesian plane. Okay, then cos of theta is just going to be equal to the adjacent. Remember, the adjacent over the hypotenuse. And notice, for this one, the adjacent side to theta is just x, and the hypotenuse is r as well. So it's going to be x divided by r, okay, in terms of Cartesian plane. Then our tan theta, which is going to be the opposite over the adjacent. Okay, this is just going to be equal to our opposite of theta, which is y, divided by our adjacent, which is x. So it's going to be y divided by x. Okay, so this is how we represent the ratios within Cartesian plane form. And one last small little thing that we need to remember when it comes to the trigonometry and angles, this is mainly looking at the angles and the relationship of the trig functions, is when we always start with our angle from the right side of the x-axis. So we always start here with 0 degrees. Okay, make it a little bit smaller so it looks like a degrees. Then we move anti-clockwise. Remember what I said earlier? Anti-clockwise is our positive direction, okay? So I'm going to do both the positive orientation and also the negative orientation. So notice that this is just a 90-degree angle, meaning the next angle from here would be 90 degrees, right? And then obviously another 90 degrees. If we add 90 with 90, we get 180 degrees. So that is basically saying that we are going from 0 degrees to 180 degrees in total. Okay? And then another 90 degrees will just give us 270 degrees. And then once again, it goes and loops all the way back to 360 degrees. Okay. So this can go and do a whole revolution, and it can be represented as 360 degrees. Okay. And then what about the opposite orientation? Let's do it in red. We're going to start at 0, and we're going to move 90 degrees to this side, meaning this would be negative 90 degrees. If we go all the way here, this would be negative 180 degrees. Okay. And then if we go all the way this side, it's going to be negative 270 degrees. And then we loop all the way back around, then it's just going to be negative 360 degrees. Okay. And then what I'm going to write down here is that with theta, we're going to have a positive orientation with theta when we go anti-clockwise. And if we go clockwise, it's going to be a negative orientation. Okay, so just remember it that way in this case. This is the cast diagram for a reason, by the way. I didn't forget about that. The reason why it's called cast is because we are actually going to be labeling it this way. First, before I get into that one now, we usually start here with C, right? C would be in this quadrant, which we actually call quadrant 4. This is quadrant 4, this is quadrant 1, this is quadrant 2, and this is quadrant 3, as you've learned in grade 10. Okay, but the cast diagram, it goes in this order. We start with quadrant 4 here, which starts with C, and then we go to quadrant 1, which is A. S goes in quadrant 2, and T goes in quadrant 3. Now it forms the word cast. And what does that actually stand for, right? The C, we know in trig, actually stands for cos. Okay? A stands for all, so all of them. S stands for sine, and T stands for tan, right? And what are we trying to say here? In these specific quadrants, we are saying that they are just all positive. So all of them are going to be positive in quadrant 1, and in quadrant 2 only sine is going to be positive, and in quadrant 3 only tan is going to be positive, and quadrant 4 only cos will be positive. So I know this is a lot on a diagram, but when we actually do the examples, you're going to see how they're actually used. So let's get into our first example. So for example 1, if sine theta is equal to 2 over 3, and theta is the element of values between 90 degrees all the way to 270 degrees, now we need to evaluate sine square theta plus cos square theta. So this is a lot to take in right now as an example, but let's work through it one by one, and let's do it step by step to make it a lot easier for ourselves. So first things first, they tell us if sine theta is equal to 2 over 3 and this interval is applied, so meaning they are telling us that theta is restricted between only the values of 90 degrees and 270 degrees included, right? It's a closed interval here. So theta cannot lie anywhere outside this interval. Meaning, if we're going to use cast diagram, we are only going to inspect the theta values between 90 degrees and 270 degrees. So when we look at this cast diagram, remember, or not cast, actually the Cartesian plane, but if we think about the cast diagram, we know that 90 degrees, positive 90 degrees is here, and 270 degrees is at the bottom here, right? Meaning we cannot work at all. We need to eliminate this quadrant and this quadrant, because notice that this is now from 0 to 90 degrees, and here it's from 270 degrees to 360, which is not in our interval. We're only working between 90 degrees and 270 degrees. and anti-clockwise as our positive orientation. Remember that. Meaning, we need to insert a radius either over here or over here. And how do we know which quadrant to put it in? Now that is when we use what else we are given, which is this one here. So the first step is to obviously look at your interval that you're given, what is the restrictions that you have, and then the next step is to use the trig ratios that you know, okay? So we know that we are working with sine theta, right? Which is 2 over 3 in this instance. And sine theta is equal to what? It's equal to opposite over hypotenuse, okay? And in Cartesian plane, do you remember that we wrote it as y divided by r? Meaning, what we can do is note that the y value, right? This is just implying to us, by the way, that 2 over 3 is equal to y over r, where we can see y is equal to 2 and r is equal to 3, okay? So y is equal to 2 and r is equal to 3. You don't really need to write this down. I'm just obviously just showing you guys the implications here, okay? Meaning, on the y-axis, we need to be 2 units up, and it's positive, by the way. It's positive 2, meaning we're going to be working in the positive y-axis. If we were to have negative 2, we would work in the negative y-axis. I hope that clears everything up. Meaning, we cannot use this quadrant because our y value here in this quadrant is negative. Okay, it's a negative y. So we have to work with the positive y values, which is this quadrant now. At least we found the quadrant that we can draw our radius. So let's start drawing our radius, okay? Our radius always starts from the origin, and then let's put it all the way here, okay? And let's say that this point here, right, this y value here is 2, what we know already, right? Y is equal to positive 2, and now r is equal to 3, meaning that our radius is equal to 3, right? And here we need to draw it, like I showed you earlier, we need to draw all the way down to the x-axis, and then show our right angle, and we're going to say that this whole side here is 2. Notice that this is parallel to the y-axis, and they're the same height, right? It's 2 units up. So meaning we have the y-coordinate for this point already, but we need the x-coordinate. And what is the x-coordinate, and how do we find the x-coordinate? Well, notice we're missing one side in a right angle triangle. And how do we find a missing side in a right angle triangle? Well, we use Pythagoras, okay? So with Pythagoras, we are going to do the following, okay? So remember that Pythagoras, in this instance, is just going to be hypotenuse squared, right? Hyp squared is equal to opposite squared plus adjacent squared. And if we were to correlate this into Cartesian, we know that the hypotenuse is just the radius, which is radius squared. The opposite is just going to be the y, because notice that for our theta, the opposite side to theta in this case here, and the theta always goes underneath the line, by the way. The opposite side is just going to be 2, so it's going to be, or we can just say y squared for now, for example purposes, and then adjacent for this one is going to be x squared, okay? And what are we trying to find? We're trying to find the adjacent, which is x. So we need to solve for x from here, okay? So we are going to get x alone. We're going to take y squared over. So we're going to minus both sides by y squared. Then we're going to have x squared is equal to r squared minus y squared. And remember that this is an instance of Pythagoras. Okay. So we have to indicate the reason that we're using this. It's because we're using Pythagoras, okay? Now we need to substitute the values that we have. We know that r is equal to 3 over here, and y is equal to 2. So meaning we can substitute. X squared is equal to r squared, which is going to be 3 squared, minus y squared, which is 2 squared. Okay. And then x squared is just equal to 3 squared, which is 9, minus 2 squared, which is 4. So it's 9 minus 4, which is 5. And then from here, we are going to have to square root both sides, okay? Because whenever you have a square, you want to get rid of that square by square rooting both sides. So we have x is equal to plus or minus. Remember, it's an even it's an even exponent. So we'll take plus minus the square root of 5. Okay. Now we need to choose which one it is. Now, if you're going to say that it's going to be positive because it's just the side of a shape, you are absolutely wrong, because now we're dealing with Cartesian planes, right? So with Cartesian planes, notice we need to be accurate to what side of the x-axis it lies. Remember, we have two possible x values for this equation. We have x equals to positive 5, root 5, or x equals negative root 5. And the thing is, we are in quadrant 2, right? Quadrant 2, notice the x values are negative, meaning we need to choose the negative version. So this implies to us that x cannot be equal to positive square root 5, but x can be equal to negative root 5. The reason why we chose that is because x-axis is negative in quadrant 2. So we're going to choose the negative value. Okay, so this one, just to make sense of it, is going to be negative root 5. And then here we have our missing x value now, negative root 5. Okay, so let me make that a little bit neater now, negative root 5 and 2. Okay, so that's our coordinate for that point there. Now remember, the main part of the question is to evaluate sine squared theta plus cos squared theta. Now, the further videos is going to tell us that this is an identity, right? So let's see what value that this gives us when we say sine squared theta plus cosine squared theta. Okay, so the reason why we found that missing x value is so that we can use our trig ratios, right, in terms of Cartesian planes, so that we have all our variables in order to substitute for our ratios, okay? So what are we actually trying to solve, okay? Remember, we are trying to evaluate sine squared theta plus cos squared theta, okay? And notice, sine squared theta is actually just the same as sine theta to the power of 2 plus cos theta to the power of 2, okay? So this, by the way, there should actually be an equal sign. Let me fix this. I know they don't really care too much about the way you notate things, but at the same time it does need to make more sense, and it's easier to write things underneath each other instead of next to each other. So in this case, we say it's equal to sine theta squared plus cos theta squared. Why is this necessary? Because now we can rewrite inside of these brackets what is sine theta. We remember sine theta is the same as y over r, okay, squared, plus now cos theta we're just going to replace with x over r from our Cartesian plane ratios, and this is squared, okay. And we now know what our y value is and our x value and our r value. What is our y value? From the coordinate point we have, x is equal, so remember this is our x value and this is our y value. So our x value is negative root 5 and our y value is 2. So y is equal to 2 and r is equal to 3, right? It's the radius. So it's 2 over 3 squared. Plus, this one is going to be x over r, which is negative root 5 over 3, okay, squared. Over here, we can use the properties of squares with fractions that tell us the following, right? We know that x over y squared is the same as x squared over y squared, right? Because the square goes into both the numerator and the denominator. So therefore, the square will go into the 2, which gives us 4, and the square will go into the 3, which gives us 9, plus the square will go into the entirety of negative root 5, and the square will go into 3, which is 9, okay? And then we just simplify here. It's just 4 over 9 plus, what is negative root 5 all squared? Well, the square affects the negative as well, meaning it's going to become positive, right? And then the root 5 to the power of 2 is just the same as 5, because they cancel out, right? The square and the square root cancel. Therefore, we just left with positive 5 over 9, and because it's common denominators, we can rewrite this fraction into 1, or these two fractions into 1. So it's going to be 4 plus 5 divided by the common denominator, which is 9, and then it's going to be 4 plus 5, which is 9 over 9, which is the same as 1. Okay, so this value gives us 1 in this case. Okay, now that we've done that example, this one is actually for you to try. So everything that I've just taught you right now is exactly what you need to answer these questions. So I'm going to read it for you. Example 2 says, if tan theta is equal to 4 over 3, okay, and cos theta is going to be less than 0, meaning it's going to be negative, right? So this less than 0 obviously means negative. So if cos is negative, then determine without a calculator the value of sine theta, which is number A, sine theta over cos theta, and B, cos theta times tan theta.